Okay, so let's start today's stream, and we'll start with demystifying QuestDB on Raspberry Pi. So I have today with me a very special guest. So he's David. David is of head of developer relations at QuestDB, and he's helping developers around the globe to manage streams of data and their devices that their devices produce. He helped to develop the very first IoT developer platform before IoT was even a thing. And yes, it's true. So you can call him the guru of IoT or whatever you want, because he has decades of experience of on from ranging from small devices to big devices, from billions of series of data. So all those things, with the experience and the knowledge, he came to this particular stream to share his knowledge, the experience on time series data and IoT, Raspberry Pi, and specifically QuestDB. So let's hear it out from David. David, over to you.
Great, thank you so much. I'm really happy to be here. This is going to be great fun. So I don't know how many people have heard of QuestDB, and I'm going to guess that it's not that many because we're fairly small and brand new. I'm going to go ahead and share my screen so that y'all can see a little bit about what's going on, and we're going to walk through a whole bunch of stuff, including running QuestDB on a Raspberry Pi. I'm going to deploy an IoT device and start writing data to it, the whole bit. We'll see how all of it goes since we're going to do it all live. You know, live demos is flying by the seat of our pants. So a little bit about QuestDB. QuestDB is an extremely fast, and I mean extremely fast, time series database written entirely in Java and based on SQL. So if you are a known SQL person, then this will be very familiar to you. You can see our homepage right now. If you like what you see, please go give us a star on GitHub. We've got our little star counter up here in the corner. And before I get started, I'm just going to give you a bit of a taste of how fast this stuff really is, because I've been doing IoT for a long time. I've been doing time series databases for quite a while, and I've never really seen anything go this fast. So this is actually our newest console, and we're running a bit of a demo here. This demo is running on the New York City taxi database, which is about 1.6 billion records. So we can run some example queries here. So let's just go sum up all of the fare amounts. So that's 1.6 billion records, and we'll go ahead and run that query. And what you'll notice here is it pops up and it tells me that the whole query was executed in 168 milliseconds. The big time difference up here where it says 571 milliseconds has a lot to do with the fact that the demo is running in a data center in the UK, and I am based on the East Coast of the US. So it's going across the Atlantic a couple of times in order to do this. But that is super fast for doing a sum over 1.6 billion rows of data. And in fact, I can do both a sum and an average. And that is about a quarter of a second to run that query. As I said, I've seen a lot of fast databases, but I've never seen anything this fast, which is why I'm here now. I think it's actually quite amazing to be able to do this kind of query and this kind of thing as fast as this. So if you have questions, feel free to pop them in the chat, and I will answer them. I've got the chat window up so I can see what's going on. Now, aside from that, since we're going to talk about Raspberry Pi, I actually have a Raspberry Pi sitting here. It's a Raspberry Pi 4. And one of the things that you'll need to do in order to run QuestDB on a Raspberry Pi is actually install a 64-bit operating system. So I'm running Ubuntu 64-bit for Raspberry Pi. And I've actually pulled the source code over, and I'm going to go ahead and build it while we talk a little bit. So this is actually going to build from source the entire database, right? And then I'll start it up, and we'll start actually sending data to it and running queries against it as that comes up. It only takes basically a few minutes to build the whole thing from source. One of the things that you'll notice is that the console on this version looks different than the console on the demo that I just showed you. And that's because the demo that's online right now is our 5.0 release. And this is the 4.2 release of the database. So I'm a few releases behind on Raspberry Pi. So a little bit about why we're doing all of this. I've been doing IoT since about 2004. And one of the big questions was always, what do you do with your data, right? And there really hasn't been many great answers to that. You can put it in, people put it in MongoDB, people put it in MySQL, people put it in a whole bunch of different places. But the thing about IoT data is that it is, by definition, time series data. Time series data is basically some data reading with a timestamp. And that's what IoT data is, right? It's a never-ending stream of readings like temperature, humidity, atmospheric pressure, CO2, whatever you're measuring, and it's a never-ending stream of those over time. And so keeping track of that is really important. And time series databases, it turns out, are really, really good at that. So that's why I got interested in time series databases, and why I think time series databases are basically a perfect fit for IoT. Yes, you can store them in other databases, but they're just not built for it. And so they're not going to perform as well. One of the other things about IoT data is that there is a large amount of it, right? I can start sending data from, 1,000 sensors, and they're sending, temperature, humidity, pressure, CO2, concentration. So let's say it's sending 5 or 6 readings once a second, every second. Once I start that, I'm pretty much never going to turn it off. So it's going to run every second endlessly. That's going to be a lot of data, and I'm going to want to be able to query that data and react to that data as quickly as possible. So if the database can't handle the ingestion of that amount of data, or it can't handle querying and getting responses from that amount of data, then we're going to have a problem. So we're just about done building QuestDB from source. And I'll go ahead and start it up. So now QuestDB is running, and I can go over to our QuestDB console, and doesn't show me much because there actually isn't anything there yet, right? So what I'm going to do right now is create a table in here so that I can start storing data. Now, I don't actually have to create this beforehand. The database will create it on the fly if I want, but I'm going to create this IoT table. I'm going to make that lowercase. I'm going to keep track of the device ID, the device name, temperature, humidity, and of course, since this is time series data, a timestamp. right? And I'm going to tell it that my timestamp is my time key, and I'm going to partition this by month. I misspelled that. There we go. Great. And now I can do a really quick query, and I can actually do it with some shorthand. I can just say IoT, and you'll see that it tells me down here that I have all my columns, but I don't have any data yet. What I do have is this little IoT device. It's an ESP8266 wireless board, which has got Wi-Fi and Bluetooth on it. And then it's got possibly the single worst sensor that I've ever come across, which is a DHT11 temperature and humidity sensor. And I'm not sure if it's the sensor or the library that goes with it that makes it so bad, but it basically has terrible readings. But I've got a bunch of them, and they're really super cheap. I think I bought the Wemos 8266 boards for about $1.50 a piece, and I think the sensors were about $1 a piece. So this is less than $3 US to put this whole thing together. And I've built this application in Arduino for this little board, and you'll see I'm using a DHT11, and I'm going to go through a little bit of this. I'm going to set up the Wi-Fi and update my time. I actually don't need the time. I can take that out. And then in my loop, I'm going to read this every 2 seconds. I'm going to get the humidity, get the temperature, and I'll print them out to the console, and we'll see this as soon as I deploy it to my sensor. And then we're going to change this to the IP address of my Raspberry Pi. Now there's a couple of ways I can do this. I can either send it to the HTTP endpoint, the REST API endpoint, or I can actually send straight line protocol. The InfluxDB line protocol is understood by QuestDB, so I can send it to the UDP port and it'll just be understood. So, and in fact, I think I can just copy and paste some code in to do that. So what we're going to do is we're going to change this code to be able to do, actually, you know what? We'll just open a different. So this is I'm going to change this to my Raspberry Pi. And I'll show you down here. I read all the values, and I'm putting them into this IoT table. And you'll notice that this looks a lot like InfluxDB line protocol. I don't know how much of you know about InfluxDB. It's another time series database, and we just accept their line protocol for incoming data. So I'm going to go ahead and deploy this to my little device here. Give me just a second while I connect to it. Unfortunately, the Arduino IDE is terrible enough that I can't bring the Arduino window over to my second monitor that I'm sharing with you, or it crashes the IDE. And there we go. But what I can do, so there you can see it's sending data, right? This is the line protocol going out. And now if I go over to my database and I run that again, or did I crash it? This is what you get when you run live. Oh. Well, what I've managed to do is find some way to crash the database every time it tries to write to it. Interesting. That's never happened before. I wonder if it's because I just built a brand new version from source. But you know what I can do? I can I will start up a version here on my local machine. While I'm doing this, I will also tell you that
So there is a question on chat also, David, like
okay,
from someone. So he asks, what are the alternatives for TSDB that can be used for IoT over here?
there are lots of alternatives for time series databases. There's OpenTSDB, there is Influx, there is Timescale, there is, I mean, there's a whole bunch of them. And each of them have sort of different features and different, different pluses and minuses. QuestDB, I think, has the best performance. In fact, I'm sure it has the best performance because I've used several of the others and I've never seen anything run quite this fast. Just 1 second while
I actually love these live demos because they break and then we fix it.
right.
So everybody who is there on the chat and who is watching live, please do share and do ask the questions, because on the basis of that, we have two giveaways and those giveaways are really awesome. I'll tell you at the end of, first giveaway will be at the end of David's session and second giveaway will be end of the stream. So David, we have a follow-up question from Suman. So
Okay.
if we need to scale up, which DB would be preferred? Something like NoSQL based, or still we would go for QuestDB or time series one? So basically the question is related to scaling kind of.
Yeah. So here's the thing with things like with NoSQL databases like Mongo. They're not built for doing time series data, right? They're built for doing, JSON object store, document store, that kind of thing. And so, yes, you can make them work, but that's not what they're built for. And so you're basically using something that is not, you're using it for something it's not built for, right? So hold on, I'm redoing something over here. So yes, you can use them, but my experience, especially with things like Mongo, is that they're super easy to use and super easy to get started with. But when you start to grow, since it's not the right tool for the job, it tends to not be able to handle things once you get going, right? So I prefer time series databases for IoT projects from the start, because you're probably going to end up there anyway. So you might as well just start there, right? And if you're looking for something that's got sort of ease of use and performance, then QuestDB is probably going to be the best answer. As I said, there are other time series databases out there. TimescaleDB is mostly open source. InfluxDB is open source. So there's different ones out there. And I think it really just depends on what you're exactly looking for in your time series database.
Yeah, and if you go to DB engines, you can see only for time series they have 30 entries over there. So there are 30 time series database that you can directly view over DB engines. So, and yes, rightly said by David that each time series DB has its own plus and minuses, but definitely when it comes to performance, so you have to make sure that you get the best performance, because that's what you look for. You want to query and you want to get the result fast.
Right. And as somebody just pointed out in the chat, most time series databases aren't actually built for ARM, and QuestDB is. We have to make some changes for the most recent version to come out. I can't seem to even get it to run on my, I'm not quite sure what version I'm running here. Oh, I see what I'm doing. I have the wrong version number in my startup, so. And I realize you can't see the mistakes I'm currently making, but
So David, does QuestDB have integration with the Flux query language?
it does not. We're entirely, it's all SQL. Okay. So most DB folks that interact with databases are very familiar with SQL.
Right.
And so writing SQL queries is fairly simple for most people who've worked on databases, and we didn't see a reason to sort of change that. Mm-hmm. So let's do this. What do you know? So I'm running this, the most recent version on my desktop here.
Can you increase the font?
I can.
Yeah. Yeah, much better.
Right. So I just ran this and it turns out I have a bunch of IoT data in here already because I started collecting it on June 4th. And I guess I stopped on the 8th, but what we can do is I'll just change that code and I'll start writing more data to it right now. And disconnect that while I do it. And we're almost there. All right. So now we go back here. We'll just get recent stuff. We might have to get more recent stuff than that. Right. So that's 49 rows. That's all the stuff we're just writing right now. Right. Super fast. 81 milliseconds. Execution time, 3 milliseconds. Right. Super fast to go get that data and start looking at it. And if I take this part out, it's almost 1 million rows, right? In almost no time. I think that's really cool because, again, when you're dealing with time series data, especially IoT data, you're typically dealing with huge amounts of it, right? This has only been running since for what, 15 days, and I've already got 1 million rows, and that's just one device. So think if I have, an IoT scale deployment of, 10,000 devices, and, over the course of 15 days, I'm going to have a lot of data to go through. And if I want to be able to query that data in something close to a time that's acceptable where I can actually get some value out of it, I'm going to need something that can query that data very, very quickly. Right? And that's what I like about this, is that it's super fast to query that data.
We have one question, David,
Okay.
from Bala. What are the security best practice to follow when collecting data from various sensor devices, and how data overlapping is handled at DB? Let's say they have 10 devices.
So security is always a concern, right? And I am currently exercising security worst practices with this, because this little device, this ESP8266 device, is terrible for security. It's got basically no ability to do almost any security at all, other than a TLS connection. So it's got almost no security. The newer ESP32s and some of the other newer devices have better built-in security. And I would strongly suggest using something that has security built in, and building in as much security from the beginning as you can. One of the problems that IoT presents is that, given the number of devices, it gives a very large attack surface for somebody to come after, making an attack. And we've seen that happen with IoT devices being turned into denial of service attack actors, and you can get a very large DDoS attack going from IoT devices. In terms of databases, that's really sort of how you want to structure your data, whether you want to put everything into one table, which is what I'm doing now with just one sensor, or whether you want to put different sensors or different segments of your IoT project into different tables, and then sort of do joins on that data as you need it. The nice thing about using SQL for your query language is that all those fancy SQL joins and things like that that you would normally use are available to you. So it's fairly easy to do a SQL join and get data from different tables to do your calculations on.
And are there any alerting capabilities from the Quest UI that you are showing? Or
right now there are not. That's something that we are working on. We are a fairly young company, so we're actively taking feedback from users on things that they would like to see the database be able to do. One of the things that's coming fairly soon is the availability of a Grafana front end, so that you can build dashboards based on the data that you're seeing, that you're collecting in QuestDb.
yeah, that would have been my next question. Like, Grafana integration would be something that people would be really interested in, especially me, because creating dashboards, and you have already the alerting capabilities in Grafana itself. So you would solve two purposes if we have the Grafana integration.
Right, I'm a huge fan of building dashboards, and so we are actively working on that right now in order to be able to support building dashboards in Grafana. But one of the reasons we wanted to get this out as quickly as we did was that we're just really proud of the unbelievable performance that we've got on this database. It's not easy to see it when I'm only looking at 1 million rows, right? I say only. But when I'm looking at 1.6 billion rows and I'm doing a query on 1.6 billion rows, then that's a little bit different, right? That's some pretty impressive performance on when you're doing 1.6 billion rows.
So David, is this data available for people to try out?
This, you mean this demo online that I'm showing right now?
Yep.
Yes, it is actually, and I may get in trouble with the folks that I work with, but it is available at try.questdb.com, port 9000. I'll put that in the chat here.
Yeah, that would be great. So that if anybody wants to try it out, that would be good.
We haven't sort of released this to the whole world yet. We've done a limited announcement of this demo. So this is sort of the sharing it a little more widely on this. But feel free to go and play around with it. I'd love to see you folks go and give us a star on GitHub, join our Slack community. If you go to our,
I think David, you
oh,
won't.
I said QuestDB.com and I meant QuestDB.io. Sorry about that.
Yeah, can you share the links with me, because I think the links are not flowing to YouTube. So you can share it to me and I can post it over there.
I can certainly do that. And if you go to our website at QuestDB.io, you can join there's a link to join our Slack. You can go and give us a star on GitHub, and join us on Slack and start telling us what you're interested in and what you'd like to see.
So we have a couple of more questions, David.
Okay.
Are there any tools to identify the IO timeouts like in MySQL?
The IO timeouts?
Yeah.
I'm not familiar with that.
Okay. And are we using any sharding on the DB side in QuestDB?
I don't believe we are right now, but that's also something that I actually have to look into. I haven't looked at, I just shared the link with you so you can put it on the, yeah, there you go.
Okay, I have pasted the link. People should be able to see now. Yes.
There you go. Do we have any other questions? I don't want to, take up your whole.
Yeah, as of now, I see. Okay, last call for questions. If anybody have related to IoT, Raspberry Pi, and specifically QuestDB. And yes, you can join the Slack of QuestDB, and David will be around. So you can ask all your queries over there if you want to try out or you're stuck at some place. So he'll be there to help you out.
And if you're having trouble with the running it on Raspberry Pi, as I was, let us know there. And I can absolutely tell you right now that as that was happening, the engineering team was looking at why it's happening and looking at a fix. So we'll have that out pretty as quickly as we can, so that we can go back to running on Raspberry Pi. Live demos are always fun, right? You never know what's going to happen.
Yeah, and that's the beauty, right? So we have live demos, things break, and that's how we fix it. So I really enjoy live demos, because that's the only way to test out things and how it really works and how it doesn't work, what all breaks, what all works. And the live debugging makes it more fun to see. Actually, we couldn't see the real fun that you were doing on the other window, so we missed that part. But surely that was an insightful session on QuestDB, and I really liked just like the tagline, and we have seen the actual demo itself of 1.6 billion rows, which is, I mean, a huge number. And on that, to get a millisecond of a millisecond read performance and whatever operation sum average that you showed, I mean, that's incredible. So that highlights the lightning fast thing written over the homepage of QuestDB.
It is really just stunningly fast.
Yeah, and I know you from before, so I know that you have worked on various other time series databases. So you actually have that particular set of knowledge, like what all what was the the time that other DBs consume, and it is actually fast. So coming from you, so and with the demo, I think it's very legit to say that yes, it is incredibly fast. And so go ahead, everyone, try it out. One last question that we have is, can QuestDB be used like for other time series databases for monitoring or other use cases?
Yes, it can. And in fact, I did not show this, and I probably could have, but I I went and just turned I have Telegraph running on my laptop, which is, what InfluxDB uses for gathering data. And I just pointed it directly at QuestDB, and it started gathering all of that and storing all that same monitoring data, performance monitoring data about my laptop in QuestDB. So to move over from InfluxDB to QuestDB for monitoring my personal laptop was literally a one-line change in a configuration file, and it started writing all that same data that it's collecting to QuestDB. So that's pretty cool.
So can we say that there will be a output plugin for QuestDB soon?
Uh, well, it turns out since we already accept line protocol, we don't need a plugin, right?
Oh,
Right now, so we accept line protocol over UDP, and we're about to start accepting line protocol over TCP. So basically, all you have to do is go in and point your output to right now a UDP endpoint for QuestDB, and it all starts going to UDP just as line protocol. So it doesn't need a plugin; it just takes line protocol.
yeah, I think that should answer your question, Mukul. So David, it's time that we do a giveaway. So how
Okay.
the plan is, so people have asked random questions. So I want to make it very fair, and so that it's very justifiable. So pick any number between say 1 to 20, because I think there will be, okay, 1 to 10. I think there are around 10 questions that people have asked. So whatever number you pick, and I'll just see who posted the question on that particular number, and he or she gets the
Let's go with number 8.
number 8. Okay. Can we see who asked the question, a question or comment, except for the moderators? Can we have one of the moderators tell us, please, who was number 8? Okay, it looks like Suman is at number 8. So, Suman, you have one coupon that you can use. So it's a $25 coupon that you can use on CNCF store. You can buy anything, and the shipping is free. So $25, buy anything from CNCF store, and the shipping is free. I'll DM you the coupon code. Be sure to give a shout out to CNCF and to the stream on Twitter. So that's enjoy your swag, and thank you for joining the stream, and keep still be here, because I have my session, and we have one more giveaway, so be here. Thank you, David. Any ending points from your side that you want to add? Any developer community or how to contribute and things like that you want to add? Just final words from you.
I will just say you can follow me on Twitter and follow QuestDB on Twitter, and I put both of those Twitter handles in the chat. And again, we'd love to have some love on our GitHub repository by stars, and we'd love to have you join our Slack channel and be part of our community.
Awesome. Thank you so much, David, for being here and coming on a Friday to do a stream with the work that you are already doing. Tons of stuff, because when a company is small, then you have tons of work that you alone have to do. You have to.
It was my pleasure. It was great to be here, and I'm happy to come back anytime.
Awesome. So people, you hear him out, just buzz him on Twitter, so that if you want to hear more things, more cool stuff, more use cases you have, just give it, and so that he can build up and show us something really cool.
Yep. All right. Thanks.
Thank you, David.
Right.
Okay, folks. So we'll head over to the next part where I'll be taking Kubernetes networking. So let me share my screen real quick. Yeah, I hope you are able to see the screen. Awesome. So today we are talking on Kubernetes networking, and very interesting topic. And I always love to talk about K8s and all the CNCF stuff that we have been doing. And yes, there's one more giveaway that we'll do at the end. Same procedure, and we'll ask one of the moderators, or if David is around, we'll ask David himself to give another number so that we can do that. So share it out so that other folks on can see it live. Anyways, the recording will be there. So some of the stuff, I have a YouTube channel that I'm running for the community every weekend, and sometimes like this, I have special guests with me on specific and cool open source technology topics. We have come this Friday, next Friday, and Sundays we'll be always doing for you. And I'm CNCF ambassador, Docker community leader, and rancher, and Influx Bangalore meetup organizer. And I'm an Influx Ace, rancher ranch hands member. So you can ask me about any of this tech. I'll try to answer best of my knowledge. So that's about me. And this is the topic. I hope we'll make things interesting because we have very less demo, just opposite to the streams that I regularly do. I have tons of demo and just 4 to 5 slides. We have more of slides over here and very less demo. I will just show you the YAML files, that's it. And that too from the Kubernetes doc, or maybe we can just create a service and we can show you. Anyhow, so Kubernetes networking is very important to understand, to see how things are working inside a Kubernetes cluster. And so what we'll cover is, first I'll tell you how basic Linux network routing works. Then we'll talk about Kubernetes networking, how one pod communicates with other pod, how one node communicates with other node, how not node communicates with the pod, and on a same network, then on a different network, how it happens. And then we'll talk about proxy. Then we'll talk about the services and endpoints and how the cluster routing works. So that's pretty much it. And yeah, I'll also touch upon different type of services that we have, like cluster IP, node port, and headless services. So if you don't understand anything right now, it's completely fine. We'll be going through that. I'll not touch base on the in-depth part of all these services and all the CNI plugins, how they work, and all that stuff, because that will be coming under kind of a deep dive session that we might do in coming weeks. If you give love to this particular stream, then definitely we'll do one more. So because you giving love to the streams tells us that you want more of this particular topic. So as much as you share and you attend live streams, so it motivates us to create more streams. As simple as that. Let me go to the next slide. So in what happens in or in your home devices, or whatever you are working on, or in the Linux VMs, how the networking works is, you say you have two hosts. So you have here host 1 and you have host 2. So you will be having a ETH0 IP over here and ETH0 IP over there. So both these hosts as of now are in one network. So consider that there are two machines which are on the same network. Now, if they are on same network, they can directly communicate with each other, and they don't have to go to something called gateways, like default gateways and external gateways. So you can directly communicate via switch. So you have host, a packet is sent. I mean, if host 1 wants to communicate with host 2, a packet is sent from switch and it goes to host 2. So this is how basic networking works. Let's see how things are working in a different network. So you have now two networks, network 1, network 2, and you have different hosts over there. This one is host 1 of network 1, host 2 of network 2. Now, host 1 from network 1 wants to communicate with host 2 of network 2. So what happens is, it doesn't know where the IP, where to send the traffic, where to send the packet, where to send the network packet. So what happens is, now the concept of router comes. So router is kind of a device, and there can be other device involved as well. So router is something which will be having the IP of which will be registering the IPs of both the networks. So it will be having two IPs of I mean, it will be getting registered with two of the networks, and then the switch will be sending the data from host 1 to the router, and then the routing tables will be there inside the router to figure out like this particular where is the destination. So basically the whole funda or the whole game lies between the source and the destination. So now the source is there, so network wants tell this is the source and this is the destination where to go, but it doesn't know which host is the destination, what is the exact destination where it has to send it. Now in router, which is connected to both the networks and the switches, so it has this particular table, the routing protocols and the routing tables will be there, so which tells okay, this particular is mapped with if it is host 1, then it is mapped with this particular IP address and it has to be sent over to this particular network. So now when the packet comes and flows from host 1, it reaches the router and it make the decision of the destination and it sends to switch. So as you can see, router connects the two networks. It gets IP for both the networks, and it has a gateway configuration for the router. So in terminology, what we say is like, uh, if a host doesn't know where to send the data, it sends the data to default gateway. Keep this in mind. If we don't know, if the host doesn't know where to send the data, it will just send to the default gateway and leave it to the default gateway to understand if it has the routing information for that particular host. So for any network with unknown IP, use router as the default gateway. So that's what you configure. And by the way, you can configure it manually. You can do, there are various commands. I have not listed them down, like IP ADDR, add ADDR, then you get add the IPs for that. Then you add the gateways for that. So you can actually manually add the gateways, or you can just add a default gateway 0000 that I'll be showing you in Kubernetes section as well. So that the any unknown IP is directly rerouted to the default gateway, and there it takes the decision. It asks the router that whether you have the information of this IP, where to send it. It says yes, I have the information. You have to send it to this particular place, this particular network. Sorry, and then it sends the packet. That's how networking is working. Looks fairly simple, but sometimes it's break, and it's very difficult to find where it break. So this is a command that you can run, root -n. So it will give you similar kind of structure, maybe one or two values here and there, but I feel it will give you a similar kind of structure. So you can go to any playground. Usually I use Katacoda in my streams. So you can go to Ubuntu Katacoda playground and immediately type route -n right away, and you will be getting similar kind of stuff. So you can see we have destination, we have gateway, we have masking, we have flags, and then we have the use of that. So what it means is the default gateway. So where the destination is 0.0.0.0, that is the default gateway. So now here will be the request that will go if any unknown IP comes to the host. So in the host, this particular default gateway is set, and the request will go to default gateway if it is not on the same network. As simple as that. Now net mask or gen mask, whatever is there, 0.0.0.0, any local network requests not in the routing table are to be forwarded to the default gateway. That's what the meaning is. And IFAs are the outbound NICs, the NIC 1 or 2, whatever they are used over there. That is the IFAs. And UG is up and the default gateway. So you can see there is something written U and G. So it is G means that this particular thing is the default gateway. You can have multiple gateways that you can define, and then you have the default gateway. So if you actually, what happens is, suppose you have on internet, you have various websites, and you want to define a gateway for that. So you can explicitly set the gateway to the outside world if you only want restricted access to one or two websites. And but it is not very feasible to keep on adding on the gateways for that particular thing. So you can directly add a default gateway, so that makes much more sense. There is a very good article on this opensource.com, that is Introduction to Linux Network Routing, which explains whatever I've explained in a fairly less amount of words, it has kind of detailed description over there. Okay, now what we have is, so in Kubernetes, what happens is Kubernetes consists of node and pods. So Kubernetes have nodes, node machines. So where you will be having master, one master will be there, and then you will be having the nodes that are connected as worker nodes, and the master and the node communication happens. And so how the node to node communication happens, first thing. So when they are on the same network, so routing gateway, it doesn't send to the default gateway or the routing gateway. It directly sends data from host 1 to host 4. So you don't need anything over there. Now, if you want to send data from pod 1 to pod 4, what happens is the pod 1 P1 of host 1 will send the data to the routing gateway, and the routing gateway will know, will be having a routing table. So the routing table will be having the information. It's similar to the Linux networking concepts. The routing table will be having the information for pod 1. So then the routing table makes the decision and sends the data to host 4. Like the pod 4 is on which IP? Pod 4 is on the IP of host 4. So it sends over there, the request over there, and from there it goes to pod 4. So this is how pod to pod communication happens. K8 service. Now what happens is we have, so think of it, you have different pods, 1, 2, 3, 4. Now what you want to do is, in actual world, in a real world scenario, what happens is you have a application that is deployed on pod P1, and so you have two replicas. So one is P1 and one is P4, and whenever you want to send the traffic, you want to send on host 1 so that it goes to pod 1, and not on host 2, so that, because if you send to host 2, then it doesn't even know what to do and where to go. So how does a application, how do we put a thing on top of the cluster that knows where to send the data when the request comes for the application? Say you have Nginx application deployed. So so what should I actually hit? And so I have 10 replicas. So I have two replicas on 4 nodes. So what should I do so that my request from my browser goes to correct host or the correct pod where actually Nginx is running? So for that, there is something called services. So services is a concept. You can use the pod IP. If you know, you can directly use the pod IP, but that's not a feasible solution because you won't be specifying the pod IP, and pod IP is ephemeral. Yeah, the pod IP may change if your pod dies and comes back up again, or if your node dies and the pod is pinned up on another host. So pod will get a different IP. So when a pod gets a different IP and you hard code it in your application to go, then your application fails. So you can't take that approach. So we need something else. And that something else in Kubernetes world is called uh, service. I just have a sip of water. Yeah. So the concept of services is how you can think of services. There can be different analogies in different people brains. Someone can think of, like, is service a load balancer? Like it balances the load because what from what I'm talking, it looks like that it is balancing the traffic where to go. Is K8 service where K8 service is sorry where it is running? Is it running on the master node, or K8 service is an internal load balancer? So let's see these three scenarios, how what actually is K8 service and what it is actually not. So first of all, if we assume that your service is a load balancer, I'm just taking an assumption. So if we assume that K8 service is a load balancer, so in scenario one, you can see this, say that this is a load balancer. Now the load balancer is routing to this particular nodes and this particular pods. So these blue ones are the pods. This is a solution that could have been used by K8s, but how can we use a solution which is so much which has so much weightage in Kubernetes, and we don't even have it as a native component? In other words, what I mean is we cannot use this solution because we need something more robust, more scalable, and as a Kubernetes component, as a Kubernetes object, not something which is outside that we have to manage. So if you have to manage an external load balancer outside of the Kubernetes cluster, then it would have been very difficult to scale that and to manage even from the load balancer perspective. In scenario two, so does that, so if it's not a load balancer, then what it is? So is it like everything goes from master? So here M is the master and these two are the worker. So in this scenario, the request is going through master and it goes to pod one. Again, it goes to master and it goes to another worker. Okay, this works, but tell me one thing, what happens if master goes down? Your service breaks. But what will happen? So we can't afford to have a single point of failure. So therefore, this method also we can rule out easily. Now, third concept, is service an internal load balancer? So means there is information about all the pods and the services on each of the nodes. Now, when the request comes on one node, node one, which is this one, so it asks, like it goes to the internal load balancer, which have information of all the all the pods where to send the request for this particular service. So it goes to pod one, and if it directly goes to host 2 and host 3, so it will directly reach out to the pods. This makes sense, and this is what exactly Kubernetes uses, but there is no, I mean, the terminology is not like internal load balancer or how it works. So we have something called kube proxy. So in Kubernetes, kubeproxy take care of the communication, and it will be helping out in having the routing tables assigned. And in the next few slides, we'll see how kubeproxy builds up the routing tables and then how the services actually work. So in this diagram, this is a, I mean, this is not very good architecture, but this is what I built in a short amount of time. So we have a person. So he makes a request, or they makes a request to API server. So basically, they do a kubectl. So kubectl run in 1.18 you don't deploy, it doesn't create deployment. So but in other versions it would have created. So kubectl run, and then you give the name, and then you give the image name, and then you give the number of replicas. So basically you are telling Kubernetes to run this particular workload of this particular image on the cluster. So now what happens is the request goes to API server. The controller manager, as soon as the controller manager gets notified that boss create these pods, so controller manager immediately create the pods which are in pending state. Now the scheduler, as soon as the scheduler gets the request, the scheduler will keep on saying that, okay, is there anything that it has run? As soon as the scheduler gets the request, it tries to find the best fit a node for that particular workload according to the algorithm, and it finds that, okay, this particular workload can easily be run on node 1. Then it schedules the pods on node 1 and the pod runs, but it doesn't run immediately. What happens is inside the node, these many stuff happens. So what happens is inside a node, so this is node 1. So request went to node 1. Now there is a component in Kubernetes which is running in every node, which is called kubelet. Now kubelet is 24/7 monitoring kube API server, telling is there anything that I need to run. As soon as it gets the request, okay, you have to run a pod with this particular image. Now, there are three things that happen. Kubelet is responsible for three things. One is creating the container. Another one is applying the network configuration. The third one is volume attach. So you, if Docker is there, or if any other container engine which respects the CRI specification, then it will use that. So assume that you have the Docker terminology concepts with you. So you have, so it tells the Docker daemon to create a container. So the Docker daemon will pull the image from the repository hub.docker.com. The nginx image is pulled, then the container is run. So that part is done. Now applying the configuration, it assigns the IP to it, and that particular part is done. Then is there any volume attached as per the CSI and if we have mentioned, so that particular part also gets done. After this, it tells the master like, "Wait, this is the pod IP that I've just created for the workload that you requested for." Now the master, or the, you can say, the Kube API server will talk to etcd, because that is the only component in Kubernetes that talks to etcd. So etcd is a database which will store the pod with the pod IP. So it's not a table. So this table is not what actually is stored. So but you can assume that it is storing the pod with the IP, with the port, whatever is there. So all the information is getting stored in etcd with respect to the pods. So that's how actually a workload runs. Now, how to distribute the traffic to specific pods? We do it with the concept of services and endpoints. In services section, when we so services is a Kubernetes object, and I can show you. Okay, I'll show you at the end, because then I have to switch over the presentation and I don't want to come back again. Let me see. I can come back again. So what we have is, I'll take the questions at the end. So I see there are some comments. Okay, would I? Yeah, Kubernetes service. I hope you're able to see the screen, because I have not shared only the presentation. This time I have shared everything. So this is how you define a simple service. So in the service, you give API version v1 and you give the kind, the metadata, what is the name of your service. Now this particular section is really important. Spec selector app is my app. So based on the selector, the services will gather the information about the pods which are matching this selector. So this is where, so now you imagine a scenario. How do I know that when I request service A, the traffic should go to pod P1 and P2? I just make sure that the selectors of the service and the pods are matching, and it will automatically pick up the pods which are matching these labels. Now, I was telling you that your pod dies. Now, when your pod dies, your IP might change, but it doesn't matter in this scenario because your label remains the same. Your selector and the labels will match, and your service will be, your endpoints will be updated with the new IP. I'll just talk about endpoints right now. So with the creation of service, there is something called endpoint which is created. So as soon as a service is created, an endpoint is also created. Now endpoint control. So what does endpoint contains? Endpoint contains the pod IP and the port. So endpoint contains the pod IP and the port. So with the creation of service, endpoint is created. Now the endpoint controller. So there is an endpoint controller that keeps updating the endpoint object with the pod IP and the port as the pods comes and goes. So very simple. I have written over there. Means the pod is coming up and dying based on different scenarios, out of memory or node failure, whatever the reason is, or maybe you have caught in the node. But Kubernetes maintains the state, so it always try to create a pod as per the previous state of the deployment or the replica set that is there. So it will store all this information, and the endpoint controller keeps looking. So kind of a watcher, you can say. So it keep watching and keep on updating the endpoints for that particular service. And you don't create an endpoint automatically. As the services are deployed, an endpoint is generated automatically. And if no pods are there, the endpoint section will be empty. If the pods matching the service will be there, the endpoint section will be getting filled up. And I can show you also this scenario when we run it a small demo. I'm not prepared a demo though, but we will try to do something. Then, so now you have a fair bit of understanding. Now let's see what all kubeproxy does in actual thing. So kubeproxy writes the routing rules on each node. So each node will be having the routing rules. So you will be having the routing table which the services will be referring, and it will know where exactly which pod on which node lies, and it will send the traffic to that particular node. It stores in the form of IP tables and in the series of IP tables that it writes. And if you have Kubernetes greater than 1.11, then it uses IPVS to write, and that is another way of writing the network packets. That's it. It also keeps a track of connection and routing. So now one important concept. Let's go back to this particular example. Now, when say it is coming from a service. Now service gives it to pod P1, and from P1 it is going via this route. Now the response also comes from this. Okay, I'll give you another example that is not a very good one. So suppose the service, uh, the request comes to the host 2. Now what happens is Q proxy already has the routing tables. So it knows on which pod it has to send the data. So that routing table will redirect from host 2. From host 2, it will redirect to host 4. So the request will directly go to host 4. But the response directly doesn't go from host 4. The response come back again to host 2 and goes from here. So this is something that QProxy does. It adds a overhead on it adds extra hop, because you have your request coming on node 2. If it would have gone directly from the pod 4, which is on node 4 or host 4, then it would have been easy. But now it again goes back to node 2, and then from here it goes to the host, sorry, to the back to the response. So it adds the extra hop, but there is something that you can use, which is, let me just find it out where I noted it. So yeah, if you give a flag traffic policy and keep it to local, then it will give it to that particular node. So you have a node, so you have a pod P1 here. So QProxy also load balances. So you have, so you say you have 4 requests coming. So now you have 4 requests coming. So it has to distribute the traffic, because it's a kind of an internal load balancer it has to act for, because you don't have any, you don't tell send traffic or every traffic on P1 on P4. So what happens is it QProxy is intelligent enough to send the request automatically to pod P1 or P4. If you want to avoid that, then you can use the some policies there, host policy, traffic policy, local, some flag is there that you can set. So if it comes to P1, then it should stay over there and not go to P4, irrespective of the traffic load balancing. So that was also another concept that I wanted to cover. There is something called service discovery that you can do with the like the service name dot local, service name dot namespace dot svc dot cluster. That also you can do. So what happens is there are 4 types of services. Now I don't have any slides for that. So let's see here itself what all services are there, if it is mentioned over there. Yeah, that's kind of very good diagram over there. So let me see. IPVS, yeah, this is the proxy, IPVS proxy mode. So where this is how the Q proxy is writing the data. Cluster IP. Okay, so we have cluster IP service, but I'm not sure. Let me search over there. Okay, what I'll do is, the best thing is, let's try to do some hands-on. Kubernetes playground. Let's see if this works. In the meanwhile, let me see if any questions are there. Yeah, so there are solutions like round robin and things like that. Okay, I think we have Bala. So our networking expert is already there in the chat. So he'll be answering all the questions as well. Okay, by default network policies are not open. Yes, the network policies question. Yes. Okay. Cool. So Bala has answered almost all the questions. And yes, Bala has done a lot of research on networking as well. So uh, thank you, Bala, for answering all the questions. And you can correct me if I'm wrong on some places in the chat itself. Okay, we are here, and I'm not sure whether. Okay, we are here actually. Let me clear the screen. Pretty slow, but if it's working, it's fine. We can make it work. Just let me disconnect and disconnect actually. Hmm. Their environment is not working, and yeah, I don't have my Docker desktop working as well. What can we try? Let's try one more time. Let me just. I hope you are able to just let me know if you are still able to see the screen. Can anyone just comment in the chat if the stream is still working? Because I just changed the network. I see no comments. Okay. Thank you. I think now it should work. Oh, okay. Let's try with play with K8s. I don't know why it should work. It should have worked. So by the way, play with Kubernetes also has been upgraded to 1.18 version. I had a talk with Marcos and it's been updated now. So pretty good. Let's try it out. But we have to create the cluster. That is the only pain. But that should not take uh, much of a time. So, but what happens is, in the meanwhile, I just explain you what cluster IP is. So, when you create a service, by default, the service is called cluster IP service. So, the service is cluster IP. Then you have node port, but cluster IP is only for internal communication. I mean, you can't expose it to the external world. People won't be able to communicate using cluster IP from the external world. It just gives you a IP which is not an actual IP, and a port with which you can communicate within the cluster. So if you have a backend and you want to connect it to that, you can do from your cluster IP within the cluster. It is able to talk. And then you have node port. Node port will actually give an external node port within the range of, I think, some 3267 and 3000, something like that. So it gives that in that particular range of ports that can be accessed with node IP and node port. So you will be having a node IP and node port. Ah, that is great. Now nothing is working. Let me. What we can do is, yeah, I have something here. Okay. Let me see if one of the cluster works now. At least I should be able to show you the services that are already there. I have one cluster over there. I think that should work. Okay, let's see some of the workloads. Maybe, yeah. Mhm. Okay, yes, that makes sense. So we have different services over there. So now what happens is I add a service record. So this is actually, okay, I just will show you the service. That is much better in a YAML file, because I wanted to show you a YAML file and not getting the cluster. Yeah. So this is a YAML file for one of the applications. So what happens is you have a API version as before, and you have a kind v1. So this is a cluster type of service, and it has these ports that we have defined, and this is the cluster IP. After creating it, get assigns the IP. You don't have to give all these information, because the resource version, self link, UUID, these things gets created when you have the uh, when you have the service created. So these things get created automatically, so you don't have to do that. So that's how the service IP is. Let me see if any node port service is there. I want to show you that node port service. Okay, all these are, I actually created a service. I don't know whether that still exists or not. Volume test is there. Mm, or what we can do is, let's try to add a record, and we'll add a node port, and then let's add a port. Let's create it. Oh, we haven't selected the target. Oops. Have to give target IP. Okay, it has created, and yes. So though this won't work, but let's see a YAML file of a node port. So what happens is I gave a type node port. It assigned it a node port with 31282. So this is an automatic assignment. If you define, then it'll take that. If you don't define, then it'll automatically pick from the range that I was mentioning earlier. So now how you can access this particular node port is using the node IP and the node port. The third type of service is called load balancer service. So if you again go here, and if I select in the advanced option, if I select it as layer 4 load balancer, then what happens is the load balancer will be of the cloud provider. So the cloud provider will be giving you the load balancer, and your then your traffic will be routed via load balancer. So basically you get an external public IPv4 IP or IPv6 IP. IPv6 I haven't tried actually, but you will get the IPv4 IP. So that you can directly, I mean, if you want to make your application accessible to the external world, you can do via that particular stuff. There is one more service which is not widely used, but yeah, which is actually used for some of the cases, which is called headless service. So headless service, what it does is it does not have IP, but what it does is it borrows the IP from the pods, from the endpoints, and the DNS decides the load balancing and not the queue proxy. So in this particular scenario, the DNS will be deciding the queue proxy, and not the sorry, not the queue proxy will load balance. The DNS will be balancing over there. So yes, the core DNS is another component of another networking component that is there, and I will cover core DNS maybe in upcoming streams. I could have actually covered. I mean, the slide was not there, so I think I missed that. So core DNS is another part where all your resolvable DNS is stored. Just for example, you can you can also call your service with cluster dot local with the service name dot namespace dot svc dot cluster dot local, thing like that. So you give a service name, then you give a namespace, then svc dot cluster dot local to get to that particular service. You can use that, and um, if you do a dig on that, you get the IP. So all those stuff you can do. So DNS is also a very core component in Kubernetes, which earlier it was kube-DNS. Let me show you itself. And now it is core DNS. Core DNS Kubernetes. That will take me to the Kubernetes homepage. I visited it many times. So you have the, okay, you have actually a task as well. So actually it is a core DNS upgrade process. About core DNS, core DNS is a flexible extensible DNS server. So it's a kind of a DNS server that maintains all the entries, and it is a replace, it was replaced by it replaced it was created to replace kubedns, but still old clusters might be using kubedns. So this is just an upgrade process, and you can see more about core dns. I think it takes you to the core dns io, and it tells you how actually the core dns server is working. So yes, it is very important part of kubernetes. What do I have? Okay, my slides are done, and so this particular session was more how the networking is working on the whole, and we haven't covered any CNI plugins. We haven't covered the demo part, because I don't know why things are not working with the either of the stuff. Maybe my network problem or something like that. But okay, I'll keep that in mind. I'll make sure that we do a demo of the services. We'll create a pod, we'll create a service, and we'll see how the traffic is getting routing. We haven't covered a very big aspect, a big topic called ingress. So that again is not what I meant to cover in this particular stream, because I just kept it on an intro level. So, but yes, when we do a deep dive session, we'll cover the ingress, the network policies, and all the stuff that were there. Let's go back to the stream itself. What are the important factors that need to consider choosing different CNI? There is a very good blog written for the comparison of different CNI plugins that are there. Like you have your Calico, Canal, Cilium, Flannel, Weave. So there is a very important, good to read documentation of that, which describes the performance. Let me just see. CNI plugin. Very good blog on, not here. Yeah, the benchmarking results of Kubernetes CNI plugins. It's not updated since 2019, I think, but that's a really good read, 9-minute read, because it what it does is, it in the end it gives you so not in the end, it gives you a very good performance review of most of the things: Calico, Canal, Cilium, Flannel, Cube Router, and WeaveNet, on different aspects, like how the network is going, and this particular thing. Yes. So overall, this is the thing, how the resources are consumed. Very good read. I'll just post the link in the chat. Very good question indeed, because in actual scenario, when you're working in a corporate world, it's very important that you choose the right networking thing, and you know the scale. So if your scale is very big, I would my personal recommendation would be Calico is very good for very huge scales, very huge Kubernetes clusters, because of its cube route, so because of its route reflector and all those stuff that it is having, and uh, very easy to set up Flannel. So those things are already there. Rancher has very good integration with Calico, Flannel, Weave. So all these things you can work. But Windows, if you are using Windows VMs, use Flannel, because that's easy to use. So depending on different permutation combination, you can select a particular CNI plugin for your Kubernetes cluster. And okay, so we have one giveaway now. I'm done for my talk, and please keep posting your questions. That's not a problem. We'll go through all the questions. And there's one giveaway that we would like to do, or we would like to do. I would like to do actually, and I say we because I consider you part of this stream itself. So we are fun community, and so we'll do a giveaway. I actually did this on purpose. I wanted to people to learn and win something and create a meetup like experience, because I did a lot of meetups. And so you have giveaways, and giveaways are very good. And Suman just won a giveaway. So the price is or the giveaway is $25 voucher, a coupon code that can be applied on cncf.store. And I'll just show you the store, and you can buy anything from here, and the shipping is free. So yes, people would have been bad if you buy of $25 and you have to pay for $75 shipping. But yeah, shipping is free. So as till the time your amount is less than $25, your shipping will be free. So you can buy anything. You can buy socks, decal packs, face masks, and things like that. So all those things you can buy. So yes, who don't want to win that? So the first lucky person was Suman, and I'll share him the code. And just give me a moment, I'll be back. So okay, so we did last time, but how I did was last time I did on the basis I asked David to tell me a random number, and his question came on that. But now what I'm seeing is from the chat that Saurabh has been here for a long time, and he has been asking a lot of questions. So I just picked Saurabh Tuck for your continuous questions that you're asking and engaging. So congratulations, Saurabh. You win the second giveaway for today's stream. And just DM me on Twitter. I'll share with you the coupon code. Make sure you give a shout out to CNCF to this stream, and so that they know that I'm actually giving these voucher away. So you just give a shout out to them, and just to tag me over there as well. And congratulations, Saurabh and Suman, for winning today's vouchers. And thank you everyone for joining the stream. We'll be back on Sunday, where we learn Golang, Docker, and Flux deep dive. And I'm doing it again and again and again. We'll be back another Friday, next Friday, on production ready Kubernetes setup and extending Kubernetes with Golang. So all those things will keep on going. So thank you everyone for joining. Thank you everyone for asking questions and answering them and keeping the stream alive. We'll be back on Sunday. Thank you. Bye bye.